Senior Research Scientist at Industrial Technology Institute, Colombo, Sri Lanka. Now I invite Professor Vrinda Morkar, Principal of DCT's Dhempe College of Arts and Science, to officially welcome all the participants of this webinar.
Thank you, Dr. Durga. Good morning, or rather good day, to all the participants from India, Japan, and also Sri Lanka, Nepal. It is my pleasure to welcome today to all of you for a national webinar on advances in material chemistry and applications organized by Department of Chemistry of Dhempe College of Arts and Science. Our college was established in 1962, soon after liberation of Goa state from Portuguese colonial rule. So it is the premier institute of higher learning in the state of Goa. We are celebrating 60 years of foundation, and to commemorate the efforts taken by founders, each department is organizing this year international or national symposium or conference. I am honored to welcome today's keynote speaker, Professor Robert Burrow, Professor of Chemistry, Universidad Federal de Santa Maria, Brazil. We are obliged that you have accepted our invitation, sir, and I appreciate the efforts taken by Dr. Bhanudas Naik in organizing this webinar. I also welcome Dr. Chinthan H.Manoratne from Sri Lanka and Dr. Rupesh Mishra, who will be joining us soon from USA. We all are eager to listen to Professor Burrow, and definitely I'm sure the participants who have joined and who will be joining in large numbers on the YouTube as well as on Google Meet will be definitely benefited by your experience and your talk. I thank Department of Chemistry for organizing this, and I am appreciating their efforts under the able leadership of our Head of Department, Varsha Virjinkar. Thanks all for joining and have a nice day. Thank you.
Thank you, Madam. Now I invite Dr. Bhanudas Naik, Assistant Professor at the Department of Chemistry of Dhempe College and Organizing Secretary of this webinar, to kindly introduce the first speaker of today's webinar, Professor Robert Burrow.
Hello everyone. On behalf of DCT's Dhempe College of Art and Science, I, Dr. Bandas Naik, welcome you to the international webinar on advances in material chemistry and applications. It is my pleasure to introduce our first speaker, Professor Robert A. Burrow. Professor Robert A. Burrow is professor at the Department of Chemistry, Center of Natural and Exact Sciences, Federal University of Santa Maria, Brazil. Professor Burrow holds PhD and a doctor in chemistry from University of Toronto, Canada, and he has a master's in chemistry from University of Toronto, Canada. His research interest is focused on the structural determination of inorganic compounds. His research explores the synthesis of new phosphonate and selenate prebinders and coordination polymers based on these prebinders. His current interest is in the synthesis of 2 and 3-dimensional polymers using rigid binders with more than one point of attachment. The compounds are primarily characterized by the single crystal X-ray diffraction as well as powder X-ray diffraction, differential scanning calorimetry, thermographic analysis, and solid-state nuclear magnetic resonance. Professor Burrow is recipient of several awards such as Walter C. Sumner Memorial Fellowship, University of Toronto Open Fellowship, Memorial University of Newfoundland Medal for Academic Excellence in Chemistry. Professor Robert Burrow has guided several master's, doctoral, and postdoctoral research students. In total, he has published 124 peer-reviewed publications and has one patent for his credit. His H index is 20. He has completed several research projects on coordination polymers and is currently working on synthesis and characterization, luminescent properties, and technological application of coordination polymers based on lanthanide phosphonates. I welcome Professor Burrow for the webinar. Professor Burrow has sent us a recorded presentation and is also present online. This topic of presentation for the webinar is on phosphonate bridge coordination polymers. If participants have any question on this topic, then they may ask their questions to Professor Burrow at the end of the presentation. I formally welcome Professor Burrow for the international welcome and all the participants. Thank you.
Good morning. It's a pleasure to start your, your meeting, the Advances in Materials, Chemistry, and Applications. I thank Professor Bernudis and Professor Principal Borker for the invitation to give this talk. This morning, I'll be talking about the phosphonate bridge coordination polymers, the work which was carried out by my students, myself, at the Federal University of Santa Maria in Rio Grande do Sul in the south of Brazil. My talk today is divided into 5 major sections. The introduction, a short section on the silver coordination polymer. There's a very interesting cobalt and nickel 2-dimensional coordination polymer with BIPI as like auxiliary ligand. The third coordination polymer is based on lead-2, and this has a reversible water uptake. And finally, I'll talk about the acknowledgements. Coordination polymers, as the name implies, are complex coordination complexes which are polymeric. And one of the essential concepts is that they must be joined by covalent bonds. Hydrogen bonds do not count. And also only exist in solid state. If you dissolve them, you necessarily must break the covalent bonds, and you'll be left with your metal centers and the ligands separated. Coordination polymers can be in 1, 2, or 3 dimensions. If it's 1 dimension, it's a chain compound. It's called a catena. If it's a 2-dimensional compound or lamellar layer compound, it's called a phyllo, the nomenclature. The 3-dimensional compounds, which are the most common, or framework compounds, are called tecto. Some recent work, a lot of recent work now is focused on 3-dimensional coordination polymers, which are porous. A coordination polymer can start out in 1 dimension only, so you just have the bridging ligand, which are these lines, which bridge between the metal centers. So they join the metal centers. And so this is a catena. You can join a series of catena with more bridging ligands, which can be the same or different, to form a layer-like structure, a laminar structure, which is called phyllo. And finally, we say you can put on the third dimension, and you will have now a framework structure. This is how they're built up. Most of the work these days are studying porous coordination polymers. This work started with Suzumi Kitagawa at Kyoto University. He calls his compounds PCP for porous coordination polymers. Omar Yagi at the University of California, Berkeley. He calls his compounds MOFs, and MOFs has the de facto name for these compounds. Gerhard Ferrer, the Institute worked at the Institut de Lavoisier in France. He called his compounds MIO for Material do Institut Lavoisier. And also, Carl-Peter Lutherhund in Oslo has a series of compounds which is called UIO. There's hundreds of, well, not hundreds, but dozens of compounds in his name. And of course, these are just a few names. Now, well, I would say dozens of researchers, groups researching this area. Honkai, the big groups now are Honkai Joe, Jeffrey Long, Omar Farhad in Northwestern, Michael Watko at Limerick in Ireland, and of course, the second generation is all their students, and now their students have another generation of people, of researchers in this area. So it's really expanded enormously in the last couple of years. The most famous coordination polymers are the MOF5, MIL100, and IU66. And of course, all the derivatives. This is an example of MOF5, and this big green ball here shows the void space in the middle, which is usually filled with solvent unless you dry it out. MIL100 has this compound. Oh, this is IU66. Has this smaller space. It's a much more stable compound. And you will now have MIL100, which is based on a 3-coordinate ligand. And most of these compounds are based on tetraphosphatic dianion, dianion, in MOF5, and of course all the MOFs compounds from Yagi, and IU666 as well is based on these compounds. Ferrer worked on these benzene tricarboxylate trianions. And these compounds are really quite, these ligands are really quite rigid, which gives a porosity. My work is based on a phosphinic acid, so which when you lose the hydrogen atoms form its diphosphonate. This compound is 4-alpha-alpha line of alpha prime xylene diol bisphosphinic acid. And this compound has easy rotation about the phosphorus carbon and the carbon-carbon to the central benzene ring here. So this compound is really quite flexible. You can form this anti-conformation, or you can form the syn conformation as well. So I've got compounds with mixed into one or the other, or both in the same compound even. A little bit more about the ligand comparing to carboxylic acids. You can see that the ligand here, you must have another organic group here. The BDC, for example, only has the carboxylic groups at the end. You have the central organic part in the middle here, whereas this has a central organic part and also has to have this extra phenyl group here because phosphorus is 4-coordinate. The geometry is quite different. This compound, the carbon atom within BDC is sp2 hybridized, so it has about 120-degree angles. And you see here it's the oxygen, carbon oxygen is about 123 degrees, whereas the phosphorus atom here is sp3 hybridized, so it has approximately tetrahedral geometry. And so you have a much closed up angle here, so it's much smaller angle. But to compensate, the carbon-oxygen distances are much shorter than the phosphorus-oxygen distances. We see that there's considerably longer, which makes the oxygen distance within the phosphonate much longer than an oxygen distance within a carboxylate group. You see that the 2.5 angstroms is about the same distance as the metal distance. The phosphinic acids are slightly stronger than carboxylic acids. My student did a potentiometric titration, so we can actually determine experimentally the pKa values, and you can see that it's 2.3 for the first pKa and 4.2 for the second pKa, which is slightly less than the pKa for the terephthalic acid or BDC. The distribution of each component can be calculated based on the pKa's, and you can see that if you have a very low pH, a very acid solution, less than pH of 1, you basically have the acid in solution, and it's actually not really soluble. It's very difficult to dissolve in a very acidic solution. But as you increase the pH slightly, you begin to form the mono anion here with a monoprotonated anion, which only exists between basically pH 2 and pH 4. As you can increase the pH above 3, begin forming the dianion, and the protonated acid goes down to 0 above pH 4. And this is quite important when you do the reactions with the compound, because you can manage to dissolve the acid here within in a basic solution. It's a slightly basic solution, but what first is formed is this compound here. So you can actually, if you don't watch out and you don't add enough base to a compound to get to pH 6, then you will have a mix between these two compounds here, the monoanion and the dianion, which will give a mixture of products in the reactions to the boys afterwards. So let's have a look at this nice coordination problem. Bernoulli's worked a little bit in this compound here. And so this is taking the ligand, azidyl bisphenylphosphinic acid. You can react with ammonia, the basic first, and you can form this nice compound here. So this is not a coordination polymer because this only has hydrogen bonding joining together. But this compound is isostructure to the compound you react with silver, interestingly enough. And the silver compound you can see is almost the same between the distance, almost the same. And this is actually a three-dimensional coordination polymer, but it's not porous. You can see that there's no space here to anything go inside. The difference, as I showed you, is very small between the two compounds. You can see that the backbone of the ligands are almost superimposed, and the silver and the ammonia cations are in the center here. The sulfur, the ammonium compound, which has hydrogen bonding, is slightly large because with hydrogen bonding, you push out the oxygen a little bit. You can see the blue here is the number is compound 1, the compound with ammonia, and you can see that the oxygen is a little bit further out. So the ammonium is slightly larger, and you have a very slightly larger volume of the cell. It's 1081 versus 945 angstroms cubic. You can see in the center of this compound, you basically have an oxygen bridge center here, and these phosphonate groups is here. They join with the organic linker to another chain of these oxygen bridged silver center. And you can see that the center of these are almost the same. This is the ammonia center. The center here is, just if you look at it in here, you can see that is it's a tetrahedral center. You have 4 oxygen atoms around that on each side, and you can see that here as well. The hydrogen bonding. Oxygen bridge center here, and this phosphonate groups is here. They join with the organic linker to another chain of these oxygen bridged silver center. And you can see that the center, these are almost the same. This is the ammonia center. The center here is, just if you look at it in here, you can see that it's a tetrahedral center. You have 4 oxygen atoms around that on each side, and you can see that here as well. The hydrogen bonding here, and the silver forms exactly the same way here. And you have about 3.1 to 3.06 angstrom distance between the silver centers, so they're really quite close. We took the opportunity to do a Forces 31 cross-polarized magic angle spinning solid state NMR of 2, which is a silver compound, and you can see that the 2 peaks here. You don't see any silver phosphorus coupling in this spectrum. And here you can see, you have 2 unique phosphorus atoms in the crystal structure, and they're really quite resolved in a solid state, even though the same group, the most phosphonate groups, but the environment is different, and that's enough to have a very slight chemical shift difference between the 2. And this here is this yellow dot is the inversion center, which makes P1, and these 2 P1s equivalent, and these 2 P2s equivalent within the cell. And in this structure here, you can see that you have what they call spinning sidebands on the side. Hope I'm showing to you. And these are spinning sidebands, which are the distance from each one is the same as the frequency of the rotor. So if you divide by the frequency, this is done at 240 megahertz. You can divide by that, and you can get this distance here. And unfortunately, we couldn't do the solid state NMR of 1 because 1 loses ammonia quite easily. It's in equilibrium, so you go back to the acid. And if you have gas evolution in the sealed rotor, it can explode. You have a lot of energy involved in the rotation, so you put a lot of energy into your compound, and this will cause the ammonia. In fact, we tried doing this, but even just closing the rotor, the cap popped off right away, even before we put it in the machine, which is really quite good, because if it remains closed, it can explode the rotor, and of course, that'll destroy the probe. And also, Burrow managed to use quantum compressor to simulate the solid state NMR, and you can see this the simulated spectrum is really quite similar to the experimental. This is experimental, and this is simulated. And second set of coordination polymers are these cobalt and nickel compounds. So beginning with cobalt and nickel ions here. If we react with the ligand, usually you form a salt, the ammonium salt of this begin with. and we use the astates here. So then you have ammonium acetate, which if you just heat them up, they'll all just evaporate out of the solution. And also we made a third ligand here, bipyridine, by 4,4-bipyridine here, to have a space here to connect between the metal centers. And actually this worked out well. With this, we have two compounds, 1 and 2 in this one here. These compounds are isostructural, they're exactly the same. They incorporate the one ligand and also a BP ligand here. And each metal center has 2 water molecules bound to them and 2 solvated water molecules to some dihydrates. And we found that if you heat these up at 200 degrees, and I'll show the TGA, which we used to discover this, we find that all the water molecules and the BP leave, and we're left with just the phosphonate cobalt structure here. Or we can, or also with nickel, the same case here, we can form this compound here. But very interestingly, we tried to just remove the BP ligand, leaving just in the water as well. And we have another compound which I called 1 double prime. And this might actually have water molecules bound to the cobalt center. We're not sure, but both of them have the same tetrahedral environment, geometry as the cobalt center. You can see by the color change. Cobalt 2 hexacoordinate is characteristically pink colored, and cobalt 2 tetrahedral with tetrahedral geometry is a dark blue color, and both these compounds are dark blue. The nickel compound is a light green color, and when you remove all the extra ligands, we have a purple colored ligand here, purple colored compound here. So this is really quite interesting. Both these get crystallized in the space group these two guys here. 2, in fact, we found a polymorph. So that's another, if you do the reaction in another way, it has the same formula, apparently, but we have not been able to characterize well the extra compound which we found. It seems to be triclinic, but the data were really not very nice. It's the extra powder diffraction is really quite ugly. So we didn't move forward with the polymorph of this compound here. And this compound here, if you remove the methanol, we actually find that in this 1 double prime, there's actually a reasonable amount of porosity. So if we have a very gentle way of removing the BP, it seems that we can leave some space in the compound to have some porous space here. Whereas if you heat it up, the construction collapses completely, and these compounds 1 prime and 2 prime are completely non-porous. And you can see the buildup of these compounds. We have basically the isostructure. The BP connects in this along the crystallographic y-axis here between the metal centers. So this can be cobalt and nickel, the isostructural. And you can see that the bisphosphonate ligand is also forms a bridge as well in this direction here. So this is actually a 2-dimensional structure only. It's a phyllo structure. And you can see better in this format here. You can see the phosphonate ligand forming this bridge here. And also we have hydrogen bonding here, which blows up the 3rd dimension. So you have the 1 minus 1 direction and 1 0 1 directions, which are different. So you have 1 in this angle here, which is a coordination polymer, and this is a hydrogen bonding between the layers. And you can see the structure is really quite complicated in situ we're seeing. Let's have a look close in that. And you can see that the ligand is here. The BP ligand is here, and the phosphonate is here, and you have the hydrogen bonding here. And if you remove the BP and the water molecules, you actually have quite a bit of space inside. You can see the space here, and this is mapped out in mercury in this yellow form here. It's a bit difficult to see. But Milky calculates you have about 24% of the volume of the crystal structure is made of the BP and the water molecules. So you can have quite a bit of porosity if you manage to remove the BP and the water molecules without the collapse of the structure. And the thermographic analysis of these compounds, this is 1 going into 1' and 2 going to 2' here. You can see that they're heating it up. As you heat up the first event, the both is basically the same. You have first the loss of the hydrated water, the 2 molecules of water, and then you have loss of the coordinated water and the BP group here. You can see that there's 2 processes happening here. You have a very fine process, the water, and the BP is a longer process. The nickel compound has a very sharp process for the water and a very large process here for the BP group. And finally, you have basically nothing happening between 250 and 500 degrees. You can see that here. There's basically nothing happening. And so this is why we can heat up 300 degrees and only these compounds here, the BP and the water will leave, and your ligand of bisphosphonate only decomposes above 500 degrees. So it's an extremely stable compound. And this forms a phosphate. And then when you get over close to 900 degrees, the phosphate decomposes and you're left with metal oxides at the very end. So they're basically the same. You can see the percent of the masses here corresponding more or less to the losses presumed. And here we did the X-ray powder diffraction. You can see that both compounds, the cobalt compound and nickel compound, have diffractograms which look really quite nice, and they're actually really similar here. And if you heat them up 300 degrees, you can see you have basically an amorphous compound here, where you have a very small amount of long-range order. These small peaks here are long-range order, which you can get from if you do a PDF analysis. Compound 2 does not remove any ligand if you wash with methanol or almost all other solvents. So only number 1 we managed to get to this 1 double prime here. And you can see that has more order to it. You can see that they have as broad peaks. So you've lost all the fine order, structure order here, but you have some long-range order that is left. You can see in the scanning electron microscope images, you can see that the compounds are like a block here, and you can have some lamellar forming here. But when you wash them, they seem to break out, and you now have very thin plates. You can see very thin plates have formed here. In the same case as 2, in this case, if you have 2, it's a blocky crystal compound, and after you're heating up, you seem to have also the very thin sheets which are formed. The nitrogen absorption analysis shows that 1 double prime here has a really nice absorption profile. And so it goes up to about 190 milliliters per gram at STP. Whereas 1 prime and 2 prime have absolutely no absorption whatsoever. They're basically the same as just a powder. So this is very interesting, and we actually want to characterize a bit better this number 1 prime with 1 double prime, because it's an amorphous compound. It's really difficult to analyze. And the third set of compounds here is the lead compound. Lead-2 is very interesting. Lead-2, in fact, has a electronic configuration based on xenonium 4F14, 5D10, and 6S2. So it actually has two electrons in a 2s orbital. So this orbital, in fact, can be stereochemically active, but not as well. So you have 2 possibilities. You have what is called homodirected, which is common for the high coordination numbers. All the ligands are uniformly spaced on the lead atom. Even the lone pair is stereochemically inert. So you basically, but it looks like that, and your your electrons lone pairs is entirely within a nest-type orbital. And if you have a lower coordination number, you can actually have a lone pair. And so this lone pair is really quite big, and it takes up one whole side of the lead atom. So you basically have all the ligands on one side and your lone pair on the other side. And this is a stereochemically active lone pair where it has a p-type character here. And this is called hemi-directed. It's very interesting that there are extremely few number of lead-2 compounds with water bound to them. And so either lead-2 or lead-4. And so this is this quote here from Jenny Glusker, done in organic chemistry. It's quite a few years back. But it really, there's almost no new compounds that made where you have more than 2 water molecules bound to lead-2. And you can see that also the other thing you have to watch out for is lead-2 ion. If you have a slightly basic solution, you form lead oxide. So you have an equilibrium between the two as well. So this is something really important. As I showed you before, the ligand you want to basify as well, the solution, to dissolve your ligand. But when you work with lead, you can't basify too much, otherwise you'll form lead oxide. So you have to have a sweet spot of your pH of the reaction. And this is the system we have here with 4 compounds here. There's another compound. I thought there was 5 compounds, but here we go. And so we start with this compound here, which is the first one synthesized. And this one actually has one water molecule for every 3 lead centers. So these dark spheres here are the lead centers. And you have one which forms a hydrogen bonding interaction to the phosphonate ligands, as well as you have forming a bridge between the 2 lead centers here in the case. In this case here, you can actually, if you form 3, let's have a look here. So if you can hydrate 1, and then slow it to 4. So if you leave 1 out, and Brazil is really humid here, we usually have a 70 to 80 to 90% humidity in here on the soil. We have really humid days here. If you leave the compound out, you get compound 4, which has a 2-to-1 lead to water ratio. It's the same structure. You can see the same basic structure, but now you have an extra water molecule inside. In this compound here, you can dehydrate 3, and you get the anhydrous compound. And if you're really, really careful, when you hydrate it, you can actually manage to get crystals of this compound here. So this is a single crystal transformations in here. It's single crystal. So we have a single crystal. We put them in a human environment. We get 4. We can actually heat it up. We can do this on the fructometer. The fructometer has a cold stream, which you can heat up to 400 Kelvin. So you can actually dry out on the cold stream to measure this. And if you're really careful, in this case here, we use just hexanes, dry hexanes. And this compound managed to pick up water from dry hexanes, but it's now in the 4-to-1 ratio, and this quickly goes to 3 if you have more water. So and this can go to 2. So this has an equilibrium depending on the humidity. So this is a really interesting system here. And also so we also found 7 compound. We have 1, 2, 3, 4, and 5 is if you have a really basic solution, you begin forming compounds with an oxo ligand. If you have a very acid, you have no product. If you have a fatty acid solution, as you saw before, you have a monoprotonated ligand. So you form 7, which is a monoprotonated compound. Fatty acid here, we have a completely decomposed. This is a PCU structure. And basically, you have this oxo ligand here, and 1 is this compound here. So you have a difference in the compound depending if you have acid, slightly acid, or basic solution here. And this compound here, and if you have a really acid solution, you have a monoprotonated ligand, and you can see that the phosphorus, the oxygen hydrogen bond is here, and this forms a hydrogen bonding interaction with a neighbor here. You can see the neighboring oxygen in the side here, and this forms chains here. This is a phyto, so it's a two-dimensional structure. And you can see the two-dimensional structure is made up with this lead atom here, and they have bonding between bridges with two ligands forming bridging, and you have a three-dimensional structure, but the third dimension is a hydrogen bonding. And this explains now the pH effect. And you can see the same diagram I showed before, where you have the acid, you have the monoprotonated base, and you have the diprotonated base here. So you can the anion here. So we're in this pH region here. And so between less than 4, between 4 and 1, less than 1 here, you have no reaction at all because you have 100% basically your diprotonated acid. But when you have the monoprotonated monoion here, and this area here, the black line here, we form number 7 here, which has the monoprotonated ligand. Between pH 4 and 6, we actually have a mixture of 1 and 7. Above 6 to 7, we only have this compound here. E8 and above, we have this compound here. And then we have a blank area here between 7 and 8 where which this work wasn't done. Let's see what compound is here. But most likely between 7 and 8, we'll have a mixture between the two. So we're beginning to have the oxo bridge. Where's the oxo in this compound here? Looking for the oxo. There's the oxo ligand here. You get the oxo ligands here. Okay. Instruction 1, so as you've seen before, has the hydrogen bonding here. You can see the hydrogen bonding between the hydrogen and the phosphonate ligand. And so for every lead to atom, to balance the charge is one bisphosphonate anion. But number of water molecules can change. You have one water molecule for 3 lead atoms in this case here. The organic pattern of the bridge, which is not shown here, which is in the 0, 1, 0, which is the crystallographic Y and Z directions. And you have in this direction here, which is the X direction, we have the phosphonate bridges here. In this compound here, you have 2 distinct lead centers. 2 of 5 coordinated with hemi-directed structures, so the approximately square pyramidal. You can see this one here and this one here. So the lone pair has a large stereo, and this one here, this one going off the side, this one is about 5 coordinate here. So this one has a sort of geometry is vacant trigonal B parameter. So this is one here, this compound here, and in this case here it's a homodirected center. You can see in this case here, if you map out, the lone pair would be about this position here, and you can calculate that out, and it's about the same position here. You can see the large home. This is the homo orbital of the lead, and you can see that it bulges out a bit more in this direction here. And this is the looking at the ligand bridging. So the oxygen, the phosphonate part forms bridges which go along the crystallographic X direction, but in the crystallographic Y, this direction here, and Z direction here, you can see that we have the organic linkers here. So this is a 3-dimensional coordination polymer. And if you look carefully, you can find a very, very small 70 angstrom void volume in the middle of this compound here. You can see here. This is why we think these compounds are really quite active, because in terms of water molecule, because water molecule has space to come in and out, and also as the ligand is flexible, it can rotate around as necessary to let the water molecules enter and leave. And you can see there's quite a structural variation as the water molecules enter. So this is the city gain. And you can see, if you look at all the four compounds here, these four compounds, you can see, looking at them, they're all basically the same. You have the same sort of structure where you have the center phosphonate bridges, and you have the longer organic spacer bridges here between the two. And so you have the anhydrous compound, the 3-to-1 lead to water, the 4-to-1 lead to water, and the 2-to-1 lead to water is all very similar. And if you look at the chains, you can see the chains are quite different. Whereas this basic structure is the same, the chains here are really quite different. You can see that here when you have the water molecule, you can see that you have this geometry here, the green geometry and the blue geometry, as the different numbers. This is 1-to-1, 1-to-1, whereas this is 2-to-1, 2-to-1, well, 4-to-2, 4-to-2, and this is 2-to-2, 2-to-2. And this one is 2-to-6, and anhydrous is the blue structure here. You can see that as the water molecules go in, you begin to change the blue geometry here, which is this one here, to the green geometry. So the 2-to-1, you have the two water molecules go in, and you also have, so they bridge two lead molecules, and you have the two lead atoms, and you have the other two lead atoms side to side here. When you're 3-to-1, then you have two sets of two lead atoms and one set of non-water bridged lead atoms, and it goes like that. It's very interesting. And if you look at the actual structure themselves, you can see, if you mark them out, how they move around. The water molecule is here in the middle, and this red is the water molecule, and the blue is without the water molecule. You can see how the water molecule goes in, and they join together. You can see there's 1, 2, and 3 here. And anhydrous has this sort of structure here. So the repeating unit is exactly the same. So the repeating unit within this compound here is exactly the same as the repeating unit in the anhydrous. So we can see the geometric change as the water uptake. In this case, looking at the water is leaving. So if you remove the two water molecules, you'll be left with this skeleton here. You can see that this oxygen here has no one to bind to. And this one here is only bound to this one, and this one has no one to bind to as well. So then you expect that this ligand will push towards this lead center, and this one to this lead center, and this will rotate the center pair of lead atoms here. As you can see, this center rotates on the side here. And this is a simulation. Let's see if the simulation is working. And this is basically beginning a solid state calculation without the water molecule and seeing how it ends up. And as you can see that you form the oxygen-lead bond. And you have a rotation of the other pair of lead atoms. So ideally, this should come to exactly the same geometry in its middle as in the sides, but it stops a little bit short. But the idea is that now we've closed up this distance here, this oxygen-lead bond has now formed, and this one in the bottom here as well. And we can see this fast uptake here between 3, which is the anhydrous, and 1. This intermediate with the 4 to 1 is not even observed because it has such a very fast lifespan. So if we have 1, which is synthesized as this peaks here, you can see I've highlighted a few key peaks in 1. If you dehydrate 1, you can see that it remains a crystalline structure. This is a single crystal to single crystal transformation. So you can see even in the powder that it's a nice crystalline structure still. But you've lost basically this peak here. This peak here has diminished, and this one is lost completely. And if you leave it in an environment with water, you can see over time, this peak goes back in again, this peak goes back in again, and this peak as well. You can see this one dislocates with the side, and it goes back in again. And after 190 minutes and a little over 3 hours, you basically have the same structure, same the powder diffraction pattern as the original compound is synthesized. So this is reversible. So you can then dehydrate it, and it goes back again. And my student, in fact, has calculated basically on the intensity. And so this is the concentration of 3 of the dehydrated compound. You can see that 3, it decreases here with a 1.7 times 10 to the minus 4 seconds minus 1 rate constant. He was using a simple pseudo first order rate law because we brought the water. And you also can have 1 in the 4, but this is a really long time. You can see that if you have 1 as synthesized and 3 is dehydrated, and then if you leave it 1 day, you're back to 3 goes to 1 again. And then after 8 days, you can see that there's almost nothing happening at 43% humidity. It's all the same. But if you have 75% humidity, as some days are like here, you can see that the next peak is now growing in around 17 degrees. And you can see here as well, the next peak starts growing in here as well, and the middle here. So, and then, even after 90 degrees, after 90 days at 75% humidity, and this is at room temperature, you can see that you haven't formed fully 4 yet. So it's a really slow process going to form. And he actually studied the kinetics of this. So if you leave it at 25 degrees, you can see that it goes in at 25 degrees and reaches an equilibrium between the two. So this is so at 6 degrees, you can see that you manage to get this. You can manage to dislocate your equilibrium to 4. But it only goes, it stops, it plateaus about 90% 4, and you remain 10% still compound 1. So you can actually work out this rate constant using this equation here between the two, the forward and reverse reactions at this equilibrium. And as in you can work out the equilibrium constant and the reverse and forward rates here. You can work them out. And basic condition shows us as this compound here, which has this oxo, where it is going? Here it is. The oxo ligand here is between 3 lead centers in a slightly basic solution. So this is something you have to watch out for these compounds here. And this is also a three-dimensional coordination polymer, where you have as well this direction here, and the next direction you have a phosphonate patch bridging the lead centers, and you have the phosphonates joined by the organic connectors in the Y and the Z directions. And here you have the unit here, which is highlighted here, so you can actually see it easier. And this compound as well, if you want to, you can dehydrate it and you form an anhydrous oxybridge compound, and this really quickly rehydrates back to 5. So this is compound 6. And this compound, we can do this on the diffractometer, just heating up this compound here with a hot stream. And you can see that as well as the other sequence of 1 to 4, it's extremely similar. You have the columns of the phosphonate bridged metal centers, and these are connected by the organic spaces, ligand spaces here. And this one as well, you have a very, very small, if you look between the anhydrous and the 5:1 ratio here, you can see that there's a very small difference between the geometry. You see that there's almost no difference at all in the geometry between of here. So it's a very small geometric change. And these compounds here, if you take the anhydrous compound, obviously, so you begin to these compounds here, and you can remove the water. You have for these compounds here, the ligand, the charged ligand leaves at about 450 degrees, whereas the 7, which has the neutral ligand, has a monoprotonated compound. You actually lose one ligand entirely. So the proton transfers, and you're left with this compound here, which is the same as compound 1, and then compound 1 will decompose down. What's left for compound 1 will decompose here at the same temperature as 1, obviously. And you can see that the nitrogen isosomes basically show almost no absorption. So 3, for example, these have to be the anhydrous compounds. 3 and 6 are basically the same as surface absorption. You have no porosity whatsoever in these compounds. We also studied the water absorption isotherms. You can see that for 6, there's a very fast absorption here. So 6 goes to 5. And so with almost no relative pressure whatsoever, so it acts like a microporous compound, this chemical reaction here. And then after that, you just have the surface water on the surface of the crystals coming in. Whereas 3 very slowly absorbs here. So until you get to 3:1 ratio. So this is 3 forms very slowly, goes to 1. And then when you get this ratio here, then it very quickly goes up and down, forming compound 4 at the end. So you basically have a half mole of water forming here, which is about 15, and then the next part here is, I guess, about 12. And here you have about 6 more, which is another third molecule more of water that goes in to form compound 4. So this is very interesting. You can show as well the water absorption of these compounds. We also did the solid state CP magic angle spinning solid state NMR. These compounds are obviously much more complicated. These have to be the most stable compounds. So we have 1, 3, and 5. And you can see that for some compounds, there are small peaks in here because they have some equilibrium and you have a little bit of water coming in or going out. So the center peaks are the principal peaks here, and you have the spinning side bands, which are coming out on the sides here. So this is the center peak of interest, and this thing is the spinning side bands are coming out here on the side. The spinning side bands are really quite important because you can model these spectra and determine the tensor the chemical shielding tensors of these peaks as well. So you can actually get more information from the solid state than the liquid. So it has a little bit of rehydration here on the side. You see the little peaks on the side here. And we can expand those a little bit. You can see that we have in six different phosphorus ligands, and you can see 1, 2, 3, 4, 5, 6 different chemical shift for the phosphorus peaks here. You always have a small amount of extra impurity on this side, which I have no idea what it is. 3, which only has 2 distinct phosphorus atoms, only has 2 principal peaks here, and you have a small amount of the hydration here, and you also have this extra peak here on this side. And 5, which has even more peaks, we have 8 distinct phosphorus atoms in compound 5. As well, you get 1, 2, 3, 4, 5 peaks, but you can see that 3 of them are much bigger than the other 3. So you have 1, 2, 3, 4, 5, 6, 7, 8. Or we only have one is bigger than the other. So, but here you have some overlapping of the peaks here. So you can't resolve all the peaks. But it's really quite difficult to get them resolved here. This is a really small peak here. And also we have this extra peak in the side. So that finishes the main part of this. And for the end, I have to thank the audience to watch this seminar. So I know Goa is a former Portuguese colony, so muito obrigado. And you now also have Canada, so I do believe that is Genevadas. And I thank again Benudis and Principal Professor Borker for the invitation to give this talk. I have to, of course, thank all the students who did this work because they're the ones who went in the lab, and Benudis was one of the people in the lab working away. And this work was funded by the Brazilian agencies, FAPERGS, which is a state agency, FINEP, which is a large equipment grant, which is paid for the large equipment and the spectrometers, CNBQ, which is a scientific agency, CAPIS, which has the scholarships, and Benudis had a postdoctorate scholarship from CAPIS. And I leave with you my contact here, my email, and everybody in Brazil uses WhatsApp these days. So here's my WhatsApp number if you need to get in contact with me. And I thank you for your again.
Thank you, sir, for the excellent presentation and providing a very thoughtful insight into the chemistry of phosphonate breached coordination polymers. Now, participants can take this opportunity to ask questions, if any, to Professor Burrow. You can unmute your mic and ask the question, or you can post your question in the chat box. Well, we had a question from Ms. Rashmi, which Professor Burrow has already answered. Another question by Ms. Monica. I'll just read out the question. Sir, why solid state NMR characterization technique of phosphonate breached compounds are important for structural studies?
Hi, Monica. It's a really nice question. Phosphonate ligands are really nice because they have the phosphorus nucleus. Phosphorus 31 is actually a really easy nucleus to study in the anatomy and in the NMR. So, and one of the big things which we found out because before our work, I didn't actually know of any other people who study these coordination polymers, the phosphorus 31 of the coordination polymers. And since the groups are so similar, I thought you might just have one big peak. But for these compounds, like the silver and the lead compounds, we actually have several separate peaks. Of course, we're using the quantum expressor to Benudis did to model these to discover which peaks really correspond to which phosphorus atoms. I didn't put any work here, but I work with some yttrium compounds, and they just have one big peak. So, so it just matters in the compounds. Different compounds are completely amorphous, and they have a very large environment, a large different environment around the phosphorus atoms. So they don't have a nice, unique environment. But when you have a stable environment, phosphorus really helps a lot. And sulfate NMR is not actually a very difficult technique to do. You just have to have the equipment, which most people don't have. And we're lucky here. We recently, about 6 years ago, we got a new 600 megahertz machine, which has a solid state option for it. So we managed to do some solid state work. So it's really quite nice.
Thank you, sir. Any more questions from the participants? We can take another question. Well, if there are no more questions, I again thank Professor Burrow for accepting our invitation. Thank you, sir.
No, thank you. Thank the Dhempe College for the invitation as well to speak to you guys. It's a really nice opportunity for me. And thanks again for everybody who's listening.
Thank you, sir.
Okay, bye then.
Yes. I feel privileged to introduce the next speaker of today's webinar, Dr. Rupesh Mishra. Dr. Mishra is currently working as a research scientist at the School of Material Engineering, Bindley Bioscience Center, Purdue University, USA. Dr. Mishra received his PhD degree from the Birla Institute of Technology and Science, Pilani, Goa campus in the year 2013. He received Sandwich PhD fellowship by French Embassy in India in the year 2011. Dr. Mishra has done his postdoctoral research on microneedle-based on-body device development for nerve agents for almost 3 years, that is from May 2016 to August 2019 at the University of California, San Diego, USA. He has also worked as research associate and research scientist in Université de Perpignan, France. Dr. Mishra has also worked as an associate professor and Ramalinga Swami Fellow at Amity University, Jaipur, Rajasthan, from the year 2019 to 2021. He has 62 publications to his credit and is a reviewer for many scientific journals like Molecular Biosystems, Journal of Material Chemistry, Journal of Alloys, Chemical Communications, etc. I now request Dr. Rupesh Mishra to start the second lecture of this webinar.
Thank you so much, ma'am, for the kind introduction. Thank you so much for inviting me over, especially to Dr. Bhanudas, who is a good friend of mine, and Professor Borkar, principal of the Dhempe College. So thank you so much. This is a great privilege to be here among the great audience, and today I will keep my talk very simple and will very crisp, maybe about half an hour, because of the time, and it's already over midnight here. And so, students, please do not consider this as a talk. I mean, this is just going to be a conversation rather. So I'm going to speak about my experiences, which I have acquired in last maybe 7-8 years overseas, especially in the wearable sensing devices and cutting edge technology. And these days, wearable on-body devices are the need of the hour, and they are very much in demand in society, because they can change the lifestyle, they can change the pattern of old people, senior citizens, and even young folks in all over the world, right? So this is very interesting, and there's a lot of opportunities to learn and to know how these devices can work, right, in a biomedical and environmental arena. So this is going to be my focus, especially environmental sectors and biomedical application. Right. So let me share my slides here. Yeah, give me a moment, please. Bhanu, please confirm if you can see my slides.
Yes, yes, Dr. Rupesh, we can see.
Thanks so much. Now this is good, right? In slide mode? In the slide mode?
Yes.
Is it looking good?
Yeah, it's looking.
Yeah, just a moment. Yeah, so I'm going to talk about smart, wearable, and disposable electrochemical biosensors for biomedical and environmental applications. So if you see in the cover slide, you can see a lot of wearable sensors, right? So starting from tattoo sensor, which is also called as epidermal sensor or biosensor, because they can uh, collect the information from human body or even animal body. Then you can see a swimming suit and there is a sensor around there. So yeah, we can develop sensor for saline water, normal water as well. And then you can see a glove sensor, right? This is one of my most highlighted work in the US. And this we have done for the Army. And then you see up there ring sensor. This is ring biosensor or ring chemical sensor. And these all are based on electrochemical transducers. So they are electrochemical biosensors. And then up there you can see a eyeglasses based biosensor, and there's a PCB board attached on there. And this we have developed for sodium, potassium, and glucose, alcohol, and vitamins detection in human tears. And this is one of the first report, where we have reported alcohol and glucose in human tears. And then you can see there are wristbands, there's an underwear sensor, there's a knee sensor. So we can have sensors anywhere, any part of the body. That's what the meaning of wearable sensors or on-body devices, right? And then you can see the ECG sensor as well. So there are some of the sensors which I'm going to briefly describe in today's talk. So I would like to start with the biosensor because I'm sure a lot of a student may be aware about the biosensing technologies, but I just briefly describe what is the biosensor. So biosensor is nothing but an analytical device. It can be small or it can be bigger in size, but these days you will see mostly a miniaturized version of biosensors. So this is an analytical device to detect the presence of an analyte, meaning that suppose if you want to detect any sample in any matrix, it can be water, it can be milk, it can be blood, it can be saliva, anything. It can be human biofluid, it can be any external fluid also. So if you want to detect any specific compound in that matrix, right? So biosensor can be of great help because biosensor consists of three things. The first thing is you have to have analyte. It can be chemical pollutant, it can be a biomolecule. So these can be an analyte, right? And then there must be a bioreceptor, because biosensor composed of two things, bio and sensor, right? So there must be an analyte which can interact with the biomolecule on top of this side, which is also called as a receptor. So when receptor will bind to chemical compounds or any analyte, they will generate specific signals, and those signals can be transmit through a transducer. And this transducer, this guy here, it can convert one energy form to another, and basically you can see some kind of signals which can be sent through the reader, and then you can see through the signal processing, you can see in a laptop or a mobile device or any smart device, right? So this is how biosensor works, and this is the mechanism to detect any compound in any given matrix, right? Then let's move ahead to the wearable sensor, because this is the main area which I'm going to highlight today. So wearable sensors are very unique and smart devices which attracted considerable attention, specifically in the scientific community these days. And these devices have shown a relevant potential for especially for continuous monitoring, because you can put these devices on body and then you can continuously track different chemicals, biomarkers in your sweat, in your saliva, or even in ISF, right, human ISF. So they have a great potential, and they have shown the relevant potential for continuous monitoring of physiological functions. For example, if somebody is running, for example, athletes. So if you can track down their, lactate concentration, sodium, potassium, yeah. So that will be really great, right? So you can really be informed, when you have such devices in the system, and they can provide real time and non-invasively um, parameters for your body, or even for like plants or animals. You can deploy these devices. So these devices are very, very useful, very handy and portable, and very, very small, small in size. These devices are, they are integrated devices basically. So they have used a lot of nanomaterials, smart materials, and that is that they can be flexible, and they are definitely miniaturized, as you can see in this slide here. This guy is a mannequin, right? We bought it from the market, and we have put a lot of sensors on this. So you see there's a SOx sensor. So we have developed a sensor where we have generated this we have harvested the energy from human sweat, and there's a lot of sweat in the bottom. So if you're putting on the shoes, you must have feel, especially in Goa condition, you have a lot of sweat, right? Because of a lot of humidity, you can have sweat. So you can generate the power from the sweat. So a stretchable chemical sensor can be one option. Then you have a glove sensor. Glove sensor can be used for different purposes. In my case, I have developed this for forensic application and for nerve agent detection. And then we have got ring sensor, I already mentioned in the first slide. Then we have metabolite sensor, lactate ECG sensor, mouth guard sensor. This is very interesting. So you can have a mouth guard sensor and integrate it with the PCB board and then device here. And this guy can detect lactate and glucose from human saliva. So basically, this is all lab to the skin journey, because earlier we used to have devices which can work in the lab, which is called lab on a chip devices. So they can work in the lab settings. But now, even we went ahead, one step further, and then we how to call it? I mean, we have miniaturized them to be put onto the body. So lab to the skin journey. And according to the survey in 2016, there's a huge market for wearable sensor, which is about $150 million in 2016. And recently, I was reading an article, and it says that it will be doubling by next year. So it is going to be $300 million in 2021 and 2022. So there's a huge market, huge potential, and there's a need, right? So this is one of the hot area these days. Then there are few examples of wearable electrochemical sensors. So wearable electrochemical sensors can be printed on different type of substrate. So for example, you can print it on the t-shirts, you can print on alumina substrate, even on a textile. So you can print this kind of sensor design on different kind of fabrics. You can have in polyester, you can have in cotton. You can put a layer first. Suppose if you want to use a textile, you can put a layer of adhesive, and on top of that you can print any design, and these designs can be made in AutoCAD or any suitable graphic software. And then once you have that, you can have the stencils, and you can print on any substrate. And this is the example of tattoo paper based biosensor. So on the tattoo paper, you can print this kind of design, right? And then you can transfer onto the body. So when you transfer onto the body, it will become an epidermal sensor or epidermal biosensor. So these are the different designs, right? Tattoo based sensor. Then skin mounted temporary tattoo electrodes, right there. And then we have also developed sensors on the bandage, on the medical bandage. As one of my paper, so we published in Health Technologies, and it is for the melanoma skin cancer, and we developed this on the bandage. So there's a lot of possibilities that we can develop these sensors on a different substrate, and provided that we can have compatibility, biocompatibility, flexibility, and stretchability, because you can develop these sensor on these kind of substrates. So for example, Kapton, for example, PET, they are flexible substrates, so you can print on them and you can deploy these devices onto the different part of body, and and they are deformative. So even if you have a regular movement of body, but still these sensor can be there, up there, and they will not delaminated, they are not routed, so they are very, very good, stable, right? They're yeah, they are compatible. So these are the beauty of such devices. Now, I mean, what can be the application of such devices? There are different applications for wearable on-body devices. For example, health monitoring. So you can detect glucose, lactate in saliva. You can detect these compounds in the urine also. Then the wearable biosensors can be used in security monitoring, especially in defense sector. For example, there's a war going on, and then there's a release of nerve gases and toxic compounds. So these kind of devices can be very useful there, right? So I'm going to show one example through my work how this can be used in security monitoring. Then agri and food analysis. So wearable sensors can be used there in agriculture sector and food analysis. I'm going to talk about this as well. And then environmental application. So detection of chemicals in vapor phase, liquid phase, even in dry phase. So we have done all three phases of analysis. And what are the advantages? So advantages are they are very specific. They are highly sensitive because they are adhering with the nanomaterials, smart nanomaterials. They are portable, of course, because you can take it anywhere you want. They can work in the extreme conditions, whether it's very humid, very warm, or very cold. They can work. They can be deployed very easily, and they are very robust. They are responding very, very fast because of the adhesion of biomolecules, and they are non-invasive because you can put it on the body. For example, tattoo paper are rich sensors. They can be put in the body, and you don't really have to insert them inside, right? So they are non-invasive. Then, yeah, so I'm going to talk about the first example, which is a glove-based biosensor. This is one of my favorite sensing platform when it comes to the wearable devices, right? So let me put on my video because I want to show you something here. Just a moment, excuse me. Can you see my video, Bano? So yeah, so I'm wearing a glove here, right here. Can you see it, Bano? Just want to verify whether you can see my video or not.
Yes, you can see.
Yeah. So this is the sensor which you see on the screen, right? Of course, this is a different design, but we have the same kind of sensor here. I'm putting on my left hand, and I want to show you how we printed here. You see, there's a 3 electrode system, right? And here you see the serpentine design. So serpentine design will provide you the flexibility, and withstand with the stretchability. So we have printed on a nitrile glove, which is a lab-based glove. So first we design this in an AutoCAD, and then we have a squeezy and screen printed machine in the lab. So, and this is the finger design which we have 3D printed, especially using a mold. So this is a mold. You fix the glove there, right? And then you print the design. So basically, you put it here, you print the design, and then we have checked the stretchability and bendability. So this gave us a good response. Even if you stretch for 50% or 100%, it will withstand the deformation. I mean, it will withstand there's no scratch, there's nothing. So very robust, as you see here, right? And then after that, we have deployed this for chemical analysis. So especially for pesticide detection in the food and different surfaces, especially wood, plastic, and stainless steel. Because in army, they are using these kind of substrate, right, for the weapons, for the their jeeps, their vehicles, the bags. So they have these substrates. So we want to make sure that we can able to detect these kind of compound on these substrate. So first we have printed, then this is the collection finger, right? And this is the working electrode, reference, and counter. This is a 3 electrode system, right? And this is based on this is a biosensor, so there must be a biomolecule. So we have immobilized organophosphate hydrolase enzyme. You can see here, OPH, organophosphate hydrolase enzyme, we have immobilized in the working electrode, right? And now the story begins here. So when this sensor will be exposed to the organic compound, which is organophosphate right here, right? Let's say on tomato, you have spiked or there's already pesticide compound. You abrasively swipe on the surface of this tomato or any fruit or vegetable, and if there is any pesticide or any organic compound, let's say methyl paraxone, you just abrasively swipe, right? And then there must be a residue already collected on this collection finger, and then you sort of join these two fingers, right? And here in on the working electrode, we provide a hydrogel, right? Agarose hydrogel. So in the presence of hydrogel, this molecule which is on the surface will diffuse through and it will reach to the working electrode, and there is an enzyme. So these two molecules, analyte and enzyme, will interact specifically, and they will generate a specific electrochemical signal, which will be transmitted through this device. This is called palm sense potentiostat, right? And then wirelessly, the data will be sent through the mobile device. And when there is a pesticide, you will see this red color curve about zero point 0.7 volt, right? And if there's nothing, you'll see this black curve, which says that there's nothing. So no alarm. And when there's a red curve, there's alarm. So that's how you can sense these kind of compound on the agriculture products or different surfaces. So this is one of the unique example of biosensing. How simply you can do this kind of biosensing on the surfaces, right? And this work was published in ACS Sensor in 2017. This is one of my very first paper after coming to the USA. And yeah, so we have executed a lot of different samples and surfaces. So apple, tomato, stainless steel, and plastic. So these are the positive samples. These are the positive samples of two different organophosphate compounds, methyl parathione and methyl paraxone. When you see this, nice peak, it means there is a compound present. If you don't see anything here, right, there's negative. So it means there is nothing. And this work was an editorial choice article in that journal, and it was highlighted more than 10 media houses and in Twitter, because somehow defense, they like this work, and ACS also, so they want to highlight this, and it spread among the society or fraternity. So this was very popular work. And after this work, we have extrapolated this this kind of biosensing application, especially on a glove platform, to the to the food sector, a food arena, we can say. So this is another example of glove devices for chemical sensing at robotic fingertip. So what we have done is we have bought it's kind of toy. This hand is kind of toy. So we got it from Amazon, I think. And this is an automatic hand, like a robotic hand. So what we did is we printed a long serpentine design. So now this time we wanted to explore more. So we wanted to detect three chemicals at the same time. So we have printed three fingers. So each finger will represent one analyte. So this finger will represent, so green, right? Green will represent the sourness. So if you want to detect how, any beverages or any food item, what is the level of sourness, what is the level of sweetness, and what is the level of spiciness, right? So when you go to the restaurant, you want to check that. So yeah, that's why we develop this kind of devices, because when you see the smart devices, you will see they are mostly physiological, they're not chemical, they're not for chemical sensing, right? So we wanted to explore a bit more in the chemical sensing area. So that's why we have come up with this idea. Now you see, so for sourness, we have chosen ascorbic acid detection. Ascorbic acid is a molecule. For sweetness, we have chosen glucose. And for spiciness, we have chosen a capsaicin molecule, because capsaicin is the responsible compound for spiciness in the food, right? And again, this is the electrochemical biosensor. So I'm not going to go in the detail that how we have done it, but I just want to showcase that how these kind of smart technologies can help people in their daily lives, right? So here, this is based on the square wave voltammetry. This is based on amperometric technique, and this is again based on the square wave voltammetry. And they are operated in a very specific manner. And we have provided a range, where we apply the voltage, and it will scan through certain parameters, and then Suppose if the molecule is available there, you will see the peak at certain potential, for example, here in about 0.2. And this is an amperometry response. So it operates in a different way where we have, we provided the potential for a fixed time. So you see this kind of curve, right? And again, for the spiciness, we have applied square wave voltammetry. So you will see this kind of uniform signature of the molecule, right? And then you sort of know, okay, the molecule is present there, and you also get to know what are the concentration of the molecule in there, in the solution or in the beverages or any food item, right? So that's how you can develop these kind of biosensors. And yeah, this is just in a cartoon to showcase how a robotic finger can work. So suppose if you have, mm, let's say, spice food, and your finger can detect. You have coffee, your finger can detect, because we also detected caffeine, and then sourness. So you have a lemonade, and you can detect that. So sweet, sour, or spicy. So your sensor can tell you, okay, this is spicy, this is sweet, this is sour, right? So this is some of the real samples we have detected. So yeah, there's some peaks are there. The important thing here is this video, which I'm going to showcase here. Let me run the video, and please pay attention to this video, because this video will tell you. Sorry, this video will tell you how we perform the analysis, right? So let me start this. Yes, please pay attention in this side. So I'm going to make a commentary here side by side. So what is in my coffee, right? You have a coffee, and now you have a robotic hand here. So the middle finger is a sweet finger, which is going to detect whether there's a glucose in the sample or not, right? So first, when we have a coffee, there is no sugar, there is no glucose, right? So you're going to see a curve here, right? You see the blue color curve. It's a small. Let me just remove this for you guys. And yeah, sorry, let me run it again. Okay. So what's in my coffee? There's just coffee, no glucose. This is sample, and this blue finger goes in, dipping into the liquid, and yeah, the analysis started. So you see the deflections, right? And for this kind of analysis, we have developed our own board. We have not bought this device from the market. We have built it in the lab, because we have a team of different people, engineers, researchers, material scientists. So yeah, so engineers have done this job, and you see this blue color curve, right? This is going on. It goes on for 120 seconds, and then it'll stop, right? No sugar. We know, because we have done a lot of experiment, and we know, based on the current values, that there is no sugar. Now sugar detection, right? So what we did is we have taken out, we have mixed the sugar, glucose especially, and we mix it, right? You see here, mixing the sugar. Now again, we are placing the finger in there. Now you will see, it goes in, analysis started. Yeah, you see it right there. Yeah, goes on, and you will see this peak will be beneath the first peak. So which shows that there's a reduction happening because of the chemical reaction, and you will have less current value. It means there's a sugar present in the sample. Like here, you have a blank and you have a sample. Similarly here, you'll see it here, right? Wait a moment. Yep. So no sugar. Why we know this? Because we have done a lot of experimenting. You see one example here. There's nothing, it's a blank, and when there is a sugar, it will go down. And yeah, there's a mechanism for this, so I'm not going to go in the detail. But when you have a glucose oxidase and glucose, there's a reaction, and we have used a Prussian blue based device. And Prussian blue is known as a catalytic oxidase, which will reduce the H2O2 produced in the reaction, and then you see this deflection at the bottom, right? So this is how we have done the analysis in the lab, and everything was done in the lab, and we have done this prototype, yeah, in the lab. Now going to the next one. Yeah, there's another example of the glove based sensor, and this time we have we have executed this glove sensor for on-site detection of fentanyl. Fentanyl is a very powerful drug. Normally, this is a drug for recreational purposes, but people are misusing it, and this is 1,000 times more toxic than morphine. So you can imagine how toxic it can be, right? So, you know, consumption of fentanyl is legal in California, because this work was done in University of California. So we have got a project from Department of Motor Vehicle, yeah, and they wanted to have a technology where they can screen people, because you can take fentanyl but you cannot drive after consuming the fentanyl. So there must be a checkpoint, right, to detect the fentanyl. So we have come up with this idea. So again, we have printed the sensor on the glove, right, and the collection pad. And again, you have a portable stat, and you can detect powder, you can detect the liquid sample as well, right? You can detect any of these two. And now, so this is a direct detection of this chemical compound. So what we did is we have printed this sensor using the screen printing machine, right? And this is based on the carbon ink. But after printing, what we have done is we have modified the working electrode using multi-wall carbon nanotube and the ionic liquid. Ionic liquid is 4,3-butyl 1-imidazolio 1-butane sulfonate. This is this is a ionic liquid which gave us higher magnitude for the sensor, for the molecule detection, right? Without this ionic liquid, you can still detect the molecule, but your magnification is not that high. So we have done some studies, and we found out that, okay, using this molecule is very, very useful. So we have used it, and we got a good success. You see here, we have got a nice calibration curve here, right? And then we have detected in powder form, and as well as in the blank sample when there is a no fentanyl. So you don't see any peak here, right? This is the oxidation peak of the fentanyl. Normally, when fentanyl oxidizes, it will convert to the norfentanyl, and this is the oxidation of norfentanyl, basically, right? So this is another example of glove-based biosensor. Now, moving to the another platform, which is the ring sensor, right? The ring form. So, for example, I'm wearing a ring. So we have developed a similar kind of ring, but this is a 3D printed ring. You see here, right? So this is the 3D printed cage of ring, and inside this cage there is a PCB board, printed circuit board, which again we have developed in the lab, right? There's a very nice design of this ring. When you put on everything in a compact device, you don't realize that there is a sensor in there, right? So this is a variable sensor ring for explosives and nerve agent detection. This is again a ACS editor choice article for the same year, 2017. And in this work, we have detected 3 compounds. The first one is organophosphate, second is uh, DNT, and third one is H2O2, because when H2O2 is accumulated in the environment, it can also act as an explosive, right, in high concentration. And this is also available in a gas form. So we wanted to develop a technique where we can detect all these 3 at the same time. And you see here, so this is the DNT peak, the reduction peak of DNT. This is the H2O2 reduction peak on Prussian blue. And this is again the methyl pyroxene, organophosphate compound. You can detect at 0.7 using carbon surfaces. So these 3 molecules can be detected using this kind of ring sensor, right? Now, this is the calibration curve of methyl pyroxene, because this was my part in the work, so I'm just taking my part. So methyl pyroxene, different concentrations. You see there's an increase in the signal, and then you see similarly the linearity, a good linearity in this side. And we have decorated this ring. You see, we can say this is kind of bindi, and looks beautiful. And even you put this thing here, still your performance will be similar to this. It has not changed you know it has not changed the performance of the ring sensor. In the liquid phase, we have tested this. So this is very beautiful example of how you can showcase the technology. Then in this video, I can show you the integration of ring sensor, how we integrated and make a compact device. So I can show you here. Please pay attention this side. Inserting electronic board inside the ring. So we have printed this this cage using 3D printing, and this is a polymeric compound, right? And this is an electronic board. Now we are assembling everything into one compact device. So you see how we are attaching it. Contacts. This is the contact for the sensors. So here this is the sensor design. This is a 4 electrode system. So you can, when you have a 4 electrode system, so you can detect 2 different compounds, because this is a 3 electrode system, but now 4, right? So in 3 you can detect 1 molecule, in 4 you can detect 2 molecules at the same time, just switching the working electrodes. And this is the side view of the device. This is the bottom view, and now this whole thing will be inserted into the ring cage. Yeah, you see, and this is the screen printed device, right? Yep, looks good. And now this is ready for the analysis. You can detect DNT, H2O2 in the vapor phase. You can detect even the nerve agents, low vaporized nerve agents using this kind of devices, right? Now, going into the another platform for wearable technology, which is a microneedle based biosensor. So before heading into this part, I want to show you something here real quick. So yeah, this is the device here. You see, this is the microneedle, and I have the same device which I have developed in the lab. You can see very small, tiny device. This can be like 100 micron size, and this is a minimal invasive. I don't want to say it non-invasive, because when you put it on the body, you will feel something. So this is a minimal invasive microneedle based devices, right? And I have another device, which is a recent device I'm working on. This is a bit bigger in the size, you see, and bit thick. So this is I'm using for the dead fish to see a chemical compound in there. So this is for the dead fish, and this can be used for the human skin, or for the plant. For plant glucose detection, we have used it, and for alcohol monitoring also. So here, real quick. So we have a device, right? And this device is a hollow device, but hollow microneedle, and there's a platinum, and Ag wires inserted into the microneedle cavity, and finally you have this kind of device: counter electrode, working electrode, and reference electrode. And yeah, here I'm showing one assembly, so which is working electrode. You have working electrode, and you modify the working electrode because you want to develop a biosensor. And when you want to develop a biosensor, you must have a biomolecule, right? So here we are using alcohol oxidase biomolecule, and then we are coating the alcohol oxidase with nephron and chitosan, and there's some layer of PPD just to cover the molecule, so that it will perform in the real sample without any problem, having a good stability, right? So that's how you sort of bond the biomolecule on top of the transducer surface, right? And then you do the reactions. So first you do the reaction in the lab conditions, to have a good calibration curve. Once you have, I think I have shown it here in the below. Yeah. So once you have a good calibration curve, so this is the calibration in buffer, and this is an interstitial fluid. So artificially prepared interstitial fluid. Calibration for the ethanol, because for alcohol we are taking ethanol here, right? So this is a very nice amperograms, right, in the both side, and you have a nice calibration curve using this device. And then we have extrapolated this into the real skin. So what we did is we have made a setup like this. So this is the microneedle piercing the skin and reaching to the artificial interstitial fluid, right? And in this artificial interstitial fluid, we have spiked ethanol. So just using the dosing phenomena, just want to show and just want to know, what is the concentration actually. So we have tested with the 3 different concentrations: 25, 50, and 75, right? And you can see a different peak as compared to the blank reading. So it's going up, right? For 25, the red color is 25, then 50, then 75. So the peaks are distinct, and you can make out, okay? So 25, 50, and 75 different concentrations. So we could able to demonstrate applicability of ethanol sensing in the real mice skin, right? And then again, this is another example of microneedle. So this is the four microneedle on the single platform. So working electrode 1, working electrode 2, and counter and reference. So in the same time, you can detect two different molecules. The first molecule is fentanyl, second is nerve agent. So you can switch the working electrode and you can utilize the same platform for different sensing of the molecules, right? And we have not done any on-body experiment. Rather, we have deployed this kind of phenomena for mimic the human skin, right? So there are different protocols by which you can mimic the human skin and demonstrate such applicability, right? But we are working on a real human skin also in this direction. And this work was published in JACS in 2020. This is another example where we can detect L-DOPA using microneedle sensor. Now I'm just going to give you the examples. I'm not going to say much. Yeah, I already took over 30 minutes. So this is the L-DOPA for Parkinson management. For Parkinson, L-DOPA is a therapy, which is provided to the patients. So it is an L-DOPA. There is a very short regimen for L-DOPA. When you insert L-DOPA for the Alzheimer patient or Parkinson patients, so there's a fast oxidation of the drug. So you need to know, how fast the drug is getting into the body and oxidizing. So for that, you need to have a sensor. It's better to know the concentration so that you can timely provide the therapeutics, right? That's why we came up with this idea. And this is a dual functionality sensor. So it means you can detect the L-DOPA in human sample in two different ways. The one way is chemical sensing, second way is biosensing. You can do it in both ways, right? So this is the example of biosensing, and this is the example of chemical sensing. And this is the calibration and some studies in the lab. Then this is the example of bandage sensor, bandage biosensor, we can say. So we have taken a medical bandage. We have printed silver inks, and then on top of that, we have printed carbon ink, and we have immobilized the biomolecule for the specific melanoma biomarker. And we have developed this very nice device. You can see here, this is the microneedle device, this is the bandage device. So two different devices for the same compound. And this is the sensor performance in the lab, and then also in the pig skin, we have done it. This is another example of microneedle. So I don't want to take much of the time. But the point is we can demonstrate a lot of different applications using such devices, such tiny devices, and they are very useful, very very important, right? They can change the lifestyle, and this is the need of the hour, right? So with this, I will stop my presentation here, right? And but if you have any question, feel free to shoot. Yeah. Thank you so much once again, Dr. Bhanudas and Professor Borkar, for the invitation. Yeah, so I stop it here.
Thank you, sir, for a very informative lecture. We thank you for making us aware about the various innovative biomedical and environmental applications of electrochemical biosensors. Now it's the time for questions from participants. Participants can unmute their mic for asking question or post them in the chat box. Well, we have a question from Professor Rani. Sir, I'll just read out the question. Please give one mechanism, say glucose detection, which will help our graduate students to understand potential of your work. Sir.
Okay. So yeah, I try to make it very simple. So let me show you something here. Yeah. For example, you have a device here, right? This is the sensor. So I'm sure you must have seen the glucose strip, glucose biosensor in the market, which is in the market, right? So this works in the same mechanism. So you have a sensor strip, and it should be a carbon based or Prussian blue based, right? So you have a glucose oxidase on one electrode, and glucose oxidase will react with the glucose. So it will interact and it will produce gluconic acid. And the same time, it will also produce H2O2, right? This is a byproduct. And some electrons will release in the reaction. So what we can do is we can target H2O2, right, for sensing. So for that, we can have two options. One option is either we can choose platinum or we can choose carbon or Prussian blue. And if you choose Prussian blue, it can reduce the H2O2. If you choose platinum, it can oxidize at certain potential. So like that, you can detect the the glucose. This is of course, this is of course the electrochemical sensing, but you can also do using optical technique, using the plate method, or using the cuvette based assay. Actually, I don't remember the dye for that, but you can mix enzymes. You can mix enzyme and substrate in one cuvette, right? And I think it's a CSPD. CSPD, that is the name of the dye. You can mix with that, and then that will give you a blue color. So when it will give you the blue color, it means you can able to reduce the H2O2. When it will not give you, when there is a no glucose, it will not give you the color. So that's how you can make it out. But I'm not sure about this optical one, but I'm sure about this electrochemical sensing.
Thank you very much. You can collaborate with some of the teachers in the Dhempe College and teach them that particular process.
Yes, sir. Sure. Yeah, sure.
Very nice. Nice presentation.
Thank you so much. Thank you so much, sir.
Yes, sir. It will be a very great opportunity for us if sir collaborates with teachers from Dhempe College for the same.
Yeah, sure. Yeah, Bhanudas is a good friend of mine. Yeah, we spent 5.5 years in BITS, and we are neighbors actually. We were, living in a hostel.
Yes.
Yeah, we are neighbors.
See, finally, you had Finally, you had to trigger our young minds.
Yes, sir. Yeah, sure.
Okay, thank you.
Yeah, please let me know, sir, if I can be of any help. It will be my pleasure.
Sure. I think the Dhempe College is quite potential in that way to trap the potential of you.
Yeah, sure, sir. Yeah, I can definitely make a visit to Goa.
That is a nice thing of you. Nice, you have to visit the college.
Sure, sir. And please feel free to contact me for any sort of discussion or any sort of collaboration.
Sure.
Yes, sir. Thank you, Dr. Rupesh Mishra, and thank you, Professor Rane, also for joining us. So we have a couple of questions in the chat box. I'll just read out a question by Shashank, Mr. Shashank. Sir, can the glove-based biochemical sensor be reused?
Yeah, it can be reused, but since it is being used for the toxic compounds, we prefer not to use it, because carbon-based inks are very economical. You can afford to make a new sensor, disposable sensor. So it's better to just dispose it off. Yeah, because it will use very small quantity of enzyme, and it is not going to be very expensive. So it's better to have a disposable sensor rather than reusable.
Okay, sir. Next question by Ritika. Sir, can carbon nanotubes be used as biochemical sensors?
Yes, definitely. Yeah, because carbon nanotubes are highly conductive, right? Nanoparticles. And if you integrate these kind of nanomaterial to any kind of sensing platform, it will enhance the detection or sensitivity of your sensor. So definitely it can be used.
Okay, sir. Next question. Which enzyme is used for nerve agent biosensor?
Yeah, so the enzyme is known as organophosphate hydrolase, right? So as the name suggests, organophosphate hydrolase, it will hydrolyze the organophosphate compound. It will hydrolase, so it will break down the molecule, right? And when it will break down, it will change the color. So upon the reaction, you will see the yellow color compound.
Okay, sir. Maybe the last question we can take up by Mrs. Varsha. What type of sensors are present in smartwatches?
And smartwatch is more physiological sensors. For example, for heartbeat, for motion tracking, it's more physiological, not chemical. That is why we wanted to explore the chemical side of this wearable devices. Those are more physical, not chemical.
Okay, so thank you for answering so many questions.
My pleasure. Thanks so much.
Yeah, thanks once again for accepting the invitation, sir.
Thank you,
I
ma'am.
think we have a question from Madam Purnakala.
Yes.
Yes.
I want applicable for for COVID-19 those this thing coronavirus detection. These sensors could be applied, which is the need of the hour for now.
Yes.
What is the thought for this?
Yes, ma'am. Yeah, actually, my current project is onto the COVID-19, so N1 gene detection, basically. So what we do is we are using this kind of devices. I don't have the exact device, but I can just tell you with this device, right? You can see this device, and so what we do is we have interdigital electrode kind of devices. Yeah, better to show this device to you, right? This kind of devices, and what we do is we print graphene here, graphene, and we immobilize the DNA molecules specific to the N1 gene. N1 gene basically is RNA, right? RNA. So when RNA will interact with the DNA, basically hybridization, so you can sense that using electrochemical techniques. So that is the mechanism we are exploring right now. But we are halfway through, and we don't have to showcase this work until it gets done. So I did not talk about it, but that's my current project. Yeah, apart from DNA, you can also choose antibodies specific to those N1 gene as antigen, and you can develop biosensors using carbon nanotube, using graphene surface, or even using the gold surface.
Thank you. Thank you for elaborate answering my question.
Yeah. Thank you, ma'am.
Thank you, Madam, Principal Purnakala Ma'am of Government College Khandora for joining us. Uh, and now I once again thank Dr. Rupesh Mishra for accepting our invitation and answering so many queries. Thank you so much.
Thank you,
So,
ma'am. My pleasure.
if all the questions are over, I think we can start the next session for today. So, I request Mrs. Manisha, Assistant Professor of Department of Chemistry, Dhempe College, to introduce the last speaker for today's webinar, Dr. Chinthan Manoratne from Colombo, Sri Lanka.
Good morning to all. It's my great pleasure to introduce the next renowned speaker, Dr. Chinthan Manoratne. Dr. Chinthan Manoratne is Senior Research Scientist in Industrial Technology Institute at Colombo, Sri Lanka. He was awarded PhD degree in Material Science from University of Colombo in 2017. He has over 17 years research experience specialized in areas related to chemistry, nanotechnology, advanced materials, ceramics, organic, inorganic nanocomposites, semiconductor materials, ceramics, graphene-based nanomaterials for applications in rechargeable batteries. He has authored and co-authored 8 international research papers, 5 international communications, and 11 local publications. He has 4 patents to his credit. He also have won many awards like DC's Award for Most Outstanding Invention, Gold Medal Winning Invention organized by Sri Lankan Inventor Commission, NRC Merit Award for Scientific Publications. He is also a member of Sri Lanka Association for Advancement of Science, member of Young Scientist Forum of National Science and Technology Commission. So now I request Dr. Chinthan Manoratne to deliver his talk. Sir?
Hello,
Yes, sir.
can you hear me?
Yes, sir. You're audible.
Okay, let me share my screen first. Hello, that sharing is Can you see my screen?
Yes, sir.
Because I can't clearly see my presentation. Okay, can you see my presentation? Hello?
Yes, we can see your.
Okay. First of all, I would like to thank Professor Vinda Boker, Principal of Dhempe College, and Dr. Bandhudas Naik, Organizing Secretary, and the organizing committee for inviting us to share our research experience on material science on this webinar. Okay. Okay, my topic is materials research initiatives for value addition to locally available minerals in Sri Lanka. Before I speak about my topic, I would like to briefly introduce about my country and my institute. Actually, you know that my country is known as Sri Lanka. Previously, it was actually known as Ceylon, and it is, you know, it's an island situated in the Indian Ocean to the south of India, and our country is actually diverse and multicultural country where the Sinhala is majority, and we have Tamils, Muslims, Burgher, and other ethnic groups. And also we have about 22 million of populations, a very small population compared to your country. And our area is about 65,000 square kilometer. So with that, I would like to very briefly introduce my institute. Actually, this is one of the main scientific research and development organizations in Sri Lanka. And it was actually known as CISIR some time ago, that is Ceylon Institute of Scientific and Industrial Research. And this comes under the State Ministry of Digital Technology and Enterprise. In 2015, we celebrated our 60th anniversary. And our actual vision is to be a center of excellence in scientific and industrial research for national development. So therefore, we do a lot of innovative R&D works, internationally competitive technical service, etc. And this is my organization structure. We are governed by chairman and the governing board, and we have under that board director general. So there are actually two main technical sections, that is R&D and technical services. So I come under this R&D area, and we have, in addition to in materials technology section, we have food technology, herbal, biotechnology, etc. And technical section, we have chemical and microbiology, materials laboratory, environment technology, petrol laboratory, etc. So let me briefly introduce my section. Actually, I come from materials technology section. You know that not only our materials technology section, the entire institute is under compliant with the ISO 9000 certification. And not our R&D section also comply with that certification, because our intention is to provide good quality R&D services. And we do a lot of R&D projects. We do analytical services, technology transfers, training programs, etc. Our actually research, the studies mainly focused on the ceramics, minerals, coating, wood and cellulose, rubber and plastic. We do also conduct training programs to undergraduate students, industrialists, university, academia, etc. And actually, we have a good set of state-of-art facilities at our section. It's a diffraction, which is equipped with high temperature attachment, scanning electron microscope, FTIR, dialodometers, particle size analyzer, based on laser diffraction, viscometers, and name to few actually. Okay. Danu, is it okay? Can you hear all? Hello?
Oh, yes, we can hear.
Okay. Now, let me start my main topic. Actually, see, I showed you that our country is small and it's an island. However, we are blessed with a lot of natural resources. Surrounding our country, there is a huge sea, the Indian Ocean, and we have a lot of rainforest, water. In addition to that, we are blessed with a lot of mineral deposits within this small country. Now, to name few, I have listed here. We have graphite, vein quartz, clay, feldspar, calcite, dolomite, mica, etc. So I think every type of minerals, I would say, available in Sri Lanka. Now, here you can see some of the very...
hello, Chinthan. Hello.
Yeah.
You cannot see the slide change. Now changing the slide.
Yeah, that is...
now you can see it.
Okay. Now it's okay?
Yes. Now it's... Yeah. Yes. Now it's okay.
All right. Okay. Sorry. Now you can see the minerals available in Sri Lanka. Soil. It's a vast, versatile materials, and one of the important of these minerals is they are found in good quality. Okay, the purity is very high, so that is the very advantage of natural minerals available in Sri Lanka. And actually, in my section, we have we are maintaining a repository of these minerals available. We collected throughout the country for our research purposes, for training purposes, and it's a kind of museum. Okay, and the reason that in my title I emphasize that initiative, because it has been a practice in Sri Lankan industrialist exporters to export these minerals without value addition. They export these minerals as raw. So therefore, that will not bring good foreign revenue to the country. And on the other hand, it's a fast depletion of these resources, because we use everything as in a short period. So therefore, I think 1 decade or more, very recently, government introduced a policy to kind of banning this exportation unless we give value addition to these minerals. So that is why institute like Industrial Technical Institute is expected to carry out certain research to give value to these minerals. So I think not only our institute, there are few institutes available in Sri Lanka. They also do different kind of studies. But at material technology at ITI, we comply with align with this government policy, started or initiated some research to give value addition to these minerals, rather exporting as it is. So that is the reason that we initiated this research. Based on now here I summarize some of industries that are based on these minerals. Like we have good ceramic industry in Sri Lanka, where some are very popular. You may heard this Noritake, Dankotu. And we have good quality clay deposit as well. So they are also using clay and other industries. And we have rubber, plastic, paint, cement, nano fertilizer, etc. This is just few of industry that I listed based on our minerals. And let me start with the graphite. Now, we actually Sri Lanka is very famous for its graphite because its purity is very high. The carbon content is about 90%, and it is found in crystalline form. Therefore, the Sri Lanka graphite, it's actually known as Ceylon graphite, and it's very famous throughout the world. And so it has been a practice until recently to export in the raw way without any value addition. So as you know that their graphite is a well-known allotrope of carbon. You know, carbon exists as diamond, lonsdaleite, fullerenes, carbon nanotube, etc. Graphene, amorphous carbon, etc. So now, so I just put this information for your knowledge, just to remind you. And graphite is found in naturally. Also, it is found as synthetically, like that. The natural also in two different ways: crystalline and uncrystalline. Okay. Now, in addition to Sri Lanka, China, India, Brazil are leaders of exporting producing graphite, and there are some other countries also in lesser amount. Producing it compared to China, India, and graphite is mainly used in very conventional application like tri-cell batteries, steel, refractories, crucible, gasket, bearing. They are actually still traditional industries. I mentioned that Ceylon graphite. It is very well known as Ceylon graphite because of its high purity and the crystalline form. I mentioned actually when the government introduced this policy, what the industry did was they just reduced particle size to show that government they have added value. So, but and they export as value added product, but that is still the graphite, and there is no such value. Considerable value addition. So therefore, it is better to produce some other products based on graphite. So that is the main issue, and this is our graphite deposit distribution in the country. It's very famous. We have two graphite mines, Bogala, Kartaga, and this is okay. Okay, now let's come to the products that we develop at material techno section. Graphene and graphite oxide are very famous now advanced materials available available throughout the world, and different people, researchers are synthesizing graphene and graphite oxide because they are very advanced material. Now, in the previous lecture, you heard that graphene can be used as sensing material like that. So the graphene is using high advanced material like transistors, high sensitive sensors, conducting films, and solar cell, etc. So therefore, we at MTS try to produce graphite oxide and graphene. Actually, here we produce reduced graphite oxide because producing a single layer graphene is not that easy. So therefore, we produce few layer graphene. That is maybe 2 to 6 layers of graphene. Still, they are in very valuable and very demand. And what is important here that the research at material techno section is we have to there are a lot of ways of making graphene and graphite oxide. There are chemical methods and also physical methods. So our intention is to optimize this process so that it will be economically viable, and also that will be an efficient way of producing graphene. So therefore, for our these production, we use modified Hammer method, and also we also put our effort to optimize this modified Hammer method by optimizing the synthesis process and also this reduction process. So that is our intention. So before I talk about deeply this study, I like to stress that the first reported graphite oxide was synthesized by Burrow in 1859. Actually, he has used Ceylon graphite, the flake graphite, in his study to produce graphite oxide. Because of as I mentioned, our graphite is very pure in high purity carbon and also crystalline nature. Okay, now in this process optimization, we take care of the particle size. Now commercially you can buy graphite powder. Now in our case, it is about 111 micrometers. Now, as you know, when you reduce particle size from large to micron and then to nano, these particles tend to agglomerate and form kind of cluster. That is the disadvantage of particle size reducing, and that will also affect the final product. So therefore, one of the objectives during our study is to optimize this particle size dispersion, or simply say break these agglomerates or clusters. So we approach two methods. One is chemical and the physical method. Chemical method, we use ethanol and tritone as kind of solvent, or maybe tritone as a surfactant. And for physical method, we use ball milling and ultrasonic vibration. And we try to optimize the particle size for our production of graphite oxide and finally graphene. Now, you can see this graph. I actually just summarized the final results. We use this ethanol or tritone as a surfactant to reduce the particles, and also we use ball milling. That's a physical one. Now you can see from this graph, this red graph shows the particle size distribution of commercial graphite, and when you reduce particle size using either chemical or physical, it is reduced. The distribution is narrow. Now you can see this ball mill graphite has a narrow distribution, and it has reduced to great extent, and followed by the ethanol dispersion. Like that, we have found that ball milling for 3 hours now is sufficient for to obtain maximum particle size dispersion, and followed by ethanol for 30 minutes, ultrasonic, etc. Now this graph shows the crystallinity has not been disturbed because of this ball milling. Because the XRD spectra obtained for this ball mill graphite and commercial graphite is almost same. Their crystallinity hasn't changed. And this SCM images show this layer structure of graphite at lower magnification and higher magnification. And this the SCM images below shows the commercial graphite has no any special shapes. They are irregular shapes. Needle, some are flake-like. But when you ball mill, their structure is damaged, and the particles tend to more spherical nature. Okay. Now what we did actually, we produced or we synthesized graphite oxide and reduced graphite oxide, that is graphene, from commercial graphite powder, that is the larger graphite powder, and the ball mill or smaller graphite powder. There you can see the clear characteristics. Now, if you look at the XRD, you can see these intensities increase for graphite oxide synthesized from reduced particle size graphite. And if you look at this UV graph, you can see this the absorption is very high in reduced particle size graphite oxide. because their activation sites are now increased. When you reduce the particle size, the reaction sites increase and the reaction takes place very efficiently. That is why you get the high absorption. And also, if you take this XRD for reduced graphite oxide or graphene, you can see very low intensity peak that represent the graphene present, and it is more reduced in the ball mill graphite. So like that, you can see a clear difference between these products based on the particle size. And now this shows the FTIR spectra of two products. You can see these functional groups are very high in ball mill graphite because a lot of reaction sites are available and lot of reaction takes place and making lot of functional group. That because of the particle size reduced, and the reaction is very efficient, and that is not available in the larger particle size. The graphite oxide produced from larger particles. Now this is FK spectra for graphene. You can see the graphene produced from reduced particle size graphite bodies almost similar to graphite, and they have very less amount of functional groups. That is a good indication that our graphene is very high in quality. Because less functional groups means the interference for late applications is minimal, especially when it comes to sensor application. Now, you can see these SCM images I took from commercial, the graphite oxide produced from commercial graphite. You can see the layers, the interlayer layers are split very nicely. And this shows this the reduced particle size graphite powder. You know, you can see the internal layers also split further. That means the reaction is has taken in a very efficient way. Okay. Now this is corresponding higher magnification images, and this is reduced graphite oxide or graphene from two sources. You can see very thin, transparent-like layers synthesized from ball mill graphite. Now, the conclusive remarks out of this study is that the particle size of graphite powder greatly affect the properties of graphite oxide and reduced graphite oxide. And so these are the products we have with us. We produce at the materials and technical section, and we also now actually produce these for our customer. When the customer requests for a certain amount, we produce commercially. These are in different forms. You can see graphite oxide in different forms, in liquid form and solid form. And this is the black one is graphene. Okay, now actually another approach of our study is to optimize the thermal reduction. Here we didn't use chemicals for reduction purpose because you know that chemical is not favorable as far as the environment is concerned, and some chemicals are expensive. Therefore, we use heating as the reduction technique. To analyze the exact conversion temperature of graphite oxide to graphene, we use the high temperature attachment that is available with our XRD machine. And here you can see that we scan our graphite oxide from room temperature to 700 at different temperature intervals, and you can see that the gradual conversion of graphite oxide to graphene, and at about 500 you can have the corresponding peak for graphene, and above that the structure would be collapsed and carbonized. So we found that the graphene conversion, graphite oxide to graphene conversion takes place at about 500 degrees centigrade. This is the corresponding despacing change and 2 theta change. You can see that graphite oxide converts to graphene through an intermediate structure. Now, to understand the exact temperature where this graphite oxide is converted to graphene, we further narrow down our temperature scanning, where we did some scan from this intervals like 300 to 500 and again 300 to 400 until 385 and 400 to 525. There you can see that at about 475, conversion of graphite oxide takes place at the 475. That is the actually a minimum temperature required to convert graphite oxide to graphene. Reduction of certain amount of temperature is also economically useful, because that is the more energy saving. And we found that 475 is the minimum temperature that is enough to convert this graphite oxide to graphene. And this is the corresponding to theta change and despacing. And you can see that 475 you can have the graphene structure. So this is actually that one study at we did at materials technology section, and we have obtained actually a few layers of graphene with the surface area of about 400 square meter per gram. And based on this research, we could publish our findings in the Journal of Material Science and Technology. You can refer this publication later for your information. And actually, we have patented this process locally, and we have obtained a patent for this process. And we have actually we have been recognized by National Research Council in Sri Lanka for our research work for value addition to graphite. Okay, now let me talk about another value addition to graphite. Actually, this product is an electrode based on graphite and clay. Before I talk about this product, I want to mention that this product is a product for our another research that I will be talking in a while, where we are trying to synthesize silicon out of quartz by electrochemical method. For this electrochemical method, we need electrodes that can be stable at elevated temperature, like 500 or maybe 700, 800. So we find it difficult to find a good electrode for our research purpose. We try to contact international sources and local suppliers, but we couldn't find anyone who can give us graphite electrode that can be used at a higher temperature. So therefore, to compensate, to overcome that problem, we at material technology section, we ourselves develop an electrode that can have that has very high conductivity and current density compared to conventional electrode like carbon or platinum electrode. So that is why we had to develop an electrode as a part of our ongoing research project. So here we actually fabricated low-cost graphite-based electrode composite for electrochemical application, especially at higher temperatures. Now I explain the background. Most of electrodes are not stable at high temperatures because in certain electrode they use organic binders. This organic part is not stable at high temperature, and the structure may be collapsed at elevated temperature, and they are not stable. So therefore, we had to develop an electrode that will withstand the higher temperature and stable at elevated temperatures. So that is the background of this value addition product. Now, so you can see this the product that we have developed, and we are seeking patent right for this. And also, if you have a partner, we can transfer this technology. Okay, and now this is the thermographic analysis of this electrode. You can see that we develop this product at about 500. Okay, with the composite of graphite and clay. And you can see this the electrical and mechanical properties. You can see that our composition, especially graphite and clay, 80 to 20, it shows a very low resistor. You can see what I would say 0.34. Yeah, ohms, and it's a very low resistor. And if you look at the strength, and you can see higher, we can obtain higher strength at this graphite to clay composition 80 to 20. Okay, and also we observed their stability in different media, like different pH, like acidic, basic, and normal media. So we observed that our electrodes are very stable any of these pH condition. That's a good indication that is very advantage for our electrochemical application. Now, the important finding of this research is, now you can see this composite. Now, the CM image B shows that we have developed, actually the clay is in nanoparticle. When you mix this the ratio and compress at the required pressure, this clay tends to make nano. So these nanoparticles are the reasons that will bind these graphite layers together. Okay, so these clay particles behave as binders, inorganic binders, and this is the graphite to clay composition, that is 20 to 80. Here you can have the large particles of clay, but when you have the 80 to 20 ratio, our graphite, the clay is in nano particles, and we for the first time we reported this how to make the clay nanoparticles with this composition. And you can see this electrochemical application. Now, we use these cyclophotographs to analyze this analyte of ammonium ferrous sulfate hexahydrate. You can see it is, almost similar to the glassy carbon or platinum. And you can see the current density is very high. It is 10 to the power -3. But the glassy carbon and the platinum for the corresponding composition is in 10 to the power -5. So you can see our graphite electrode, even though it's a composite of nanoclay, it's shown very high conductivity and a good behavior of cyclic nature. And also we try to observe this sensitivity towards the different ions using these electrodes. Now you can see our graphite composite clay shows very high sensitivity towards these analyte, inferring that our product is very far ahead compared to platinum electrode or platinum electrode or glassy carbon electrode. Hello. Hello. Hello.
Oh, hello.
Oh, can you hear me?
Yes, yes, yes.
Okay. Are you following?
Yes, yes. You can repeat it.
Okay. Now, so I was talking about the sensitivity towards these different ions. You can see that our product has greater sensitivity towards these ions compared to corresponding glassy carbon or platinum. So, and another finding that we polymerize aniline using this electrode. Now you can see this the cyclic the voltograms for this study is almost similar to glassy carbon and a little bit differ from the corresponding platinum. And typical oxidation and reduction you can see, and we have got very dense polyaniline structure deposit on the this working electrode. So now it is shown that our electrode is far good compared to this commercial available platinum electrode or basic argon. And most important thing is very low cost at the production. So that's a very important aspect. So we have published this data in electrochemistry communication and also one peer-reviewed journal. So you please refer this publication for further analysis, for further data. Okay, now, so these are actually the value-added product based on graphite that is available in Sri Lanka. Now, another major project that I have worked as a principal investigator at material section is extracting silicon, the silicon metal out of quartz. You know, quartz as of graphite, the Sri Lankan quartz is very famous worldwide because high purity. Its purity, I would say, about 99%, 99 plus, and they are very crystalline form. So therefore, I think especially Japan and maybe other developed countries, they use Sri Lankan graphite to extract silicon out of this quartz. You know, the silicon is a very widely used material as semiconductor in everywhere, and so therefore, rather exporting these minerals as raw, it is our nature. It is our responsibility as scientists and institutes like ITI to start or initiate at least kind of research that will direct towards this advanced material. Now you can see this Sri Lanka. You know, it's the quartz is available as mountains. We have one pink quartz. It is said that these quartz are actually used in your Taj Mahal. Some construction in Taj Mahal, they have got received our quartz. It is said in the history. Anyway, now we have mountains of quartz with high purity. And you know, it's general applications in paint, glass, electrical and electronic applications as gems and etc. Now, when it comes to green energy and solar grade silicon, so it is essential to have silicon with high purity, like 6N. That means 99.969. So that much of purity is essential, especially in semiconductor material development. So it's a challenge, and our target is in this project to complete with maybe 60 to 70 success. And actually, some time ago, we tried to make a collaboration with Kunming University in China, and due to some other reason, it couldn't be materialized. But I think let's see if we can have collaboration with you on some other way, we can make a good future. So our intention here is to at least produce silicon electrochemically using locally available quartz. Now it is still going on, and so this is the potential of solar grade silicon and solar energy, because you know in India, Sri Lanka, like we have high solar radiation. So I think future has to be based on solar power for either electric generation or some other application. So now this is our project objective. This is the quartz, and this is our final silicon. It's not an easy task, but I think actually we have succeeded in some other way, in halfway, and let's see during the course of next year we can have some other output. Now, you know, there are some conventional methods to silicon production, like Swarovski process, carbothermic process. Still, they have impurities. To have this 6N purity, it's not easy. And the purification of silicon is far energetic, and it's a very difficult, complicated process. So we thought that if we can extract silicon electrochemically, we can have a very purified form of silicon, because the electrochemical reaction takes place at a specific conditions. That you know, at specific so that you can exactly extract silicon out of SiO2. And so actually we developed a special laboratory for this project, and we name it as Clean Energy Laboratory, and we opened that laboratory with the inauguration of chairman of ITI and the ministry secretary 3 years back. And this is 6.6 billion in Sri Lankan rupees project. And so actually we observe that we can go to our target. As I mentioned, at least to 60 to 70% target is achieved, then our goal is achieved. So that is our intention. Now you can see we have developed a special reactor for this project, special design made by ourselves, and this special laboratory for this project. And so, as I mentioned, this is still ongoing. So we did some preliminary studies like characterization of quartz and the behavior of particle size, how they impact at some elevated temperatures, and their thermal behavior at conversion temperatures. And as I mentioned, this is actually an electrochemical process. We use electrolyte like calcium chloride, and then how this calcium chloride behave at some elevated temperatures like that. So we did some preliminary studies, and interestingly, we have found some data that are worth publishing, and we have made several publications out of these preliminary studies. Okay, now this is activity flowchart for this project. I have just shown you in the flow diagram. This is actually our starting material quartz, and this is how the final product silicon. And this is actually characterization of raw quartz, and we have completed this thing. And the star mark shows that we have made some publication out of this thing. And this electrolyte, we use calcium chloride, and still some studies are going. And so this is the further graphical representation of our porous process. This is quartz powder, and we use this SiO2 as quartz pellet for reduction, electrochemical. And this is our furnace, and we have 3 electrode system, and this is specially designed for our process that can withstand high temperatures, like maybe 700, 600, or maybe 900. And this is our final silicon. And this is the electrochemical reactor specially designed for this research. And I think we are hoping to apply for patent for this reactor. And I mentioned that in my previous value-added products, the graphite electrode. This is where we need some electrode that can be used in high temperature. So we developed this electrode for our electrochemical furnace. So that project has also been completed. So, and this is our basic preliminary studies for quartz, and we studies their particle behavior when you reduce the particle size and their microstructure using this particle size analysis, morphology, and so on. And we use ball milling for reducing particle size and optimize their properties. And you can see when you ball mill quartz for 360 hours, you can reach 96% of particle size reduction. You can see this. This is the corresponding particle size. The average size is 36, and it has been reduced to 1.3 micron. And interestingly, we have observed that nano quartz in this study. So that is the one of good findings that shows that this technique can be used for other minerals as the way of producing nano particles. Now you can see this homogenizing of distribution at 360. And we, with the progressively, we have reached 96% particle size reduction and symmetrical particle size, spherical particle size, and uniformity of the size distribution within the sample. Now you can see these corresponding SEM images at each time interval. Now you can see that 360, we will have spherical particles. that is very uniformly distributed, and you can see nanoparticles as well. The raw quartz is in elongated. I mean, there is no specific shape. Now, when you look at the XRD, you can see up to 260 hours of ball milling, there is no contamination due to these balls. Now, we use alumina balls in this ball milling, but after 260 hours of ball milling, you can see alumina contamination, but it is very negligible, very low amount of contamination. You can see this very small hump appearing near to this quartz piece. It can't be even distinguished. Very small amount. And this is the normal composition of quartz that used in our study. And this shows that after 260, some level of alumina contamination can be observed, but it is also, it's very less and less than 3.3. And when you study this microstructure, you can see that because of this ball milling, the microstructure is not disturbed. Their unit cell volume is almost same at each 10 hours to 360. But however, you can see some the microstructure like strain, the bone, the micro size strain, and some displacement can be seen. But overall, there is no cell volume change. Now, for that, we used XRD graph for this peer-to-peer microstructure analysis, where we employed the Scherer method and Williamson-Hall method for both crystalline size and that is strain to understand their structure. And we, based on these data, we calculated dislocation density. Because it is essential to know this the microstructural behavior at elevated temperature, because our final overall the electrochemical reaction takes place at elevated temperature. So we should know what will happen within these materials at that temperature. So that is why we study this basic kind of preliminary data for our next level research output. Now you can see that the microstructure based on this ball milling has been increasing because of this ball milling, and crystalline size reduced enormously. That is strain gradually increasing. So we calculated these things using both methods, like Scherer method and Williamson-Hall method. And so after 360, we observe uniform crystal strain and isotopic nature of the material. So these are the Williamson-Hall graph that we plotted at each time, and you can see during the 360 ball milling, the data is scattered very narrow. Very narrow distribution. So that shows the uniform nature of symmetry after 360 hours of ball milling. So therefore, by studying this, we can conclude that this prolonged milling can often induce crystal defects in ground cores, and that produces sustainable decrease in both crystallinity and crystalline size. And okay, now I mentioned that we still study some basic information on this material, and next we actually studies the thermal behavior of quartz at high temperature. This. There are certain studies if you look at the literature, where this quartz from alpha to beta. There are a lot of studies available. But however, for the first time, here we report the Williamson-Hall method to explain the variation in lattice strain, crystalline size, and dislocation density. So we have found that some interesting information when we study the thermal behavior of quartz. Now this is alpha quartz at room temperature, and this is beta quartz, and it goes through an intermediate product. You know, this is a corresponding XRD spectrum for alpha quartz and beta quartz. And we did some thermographic analysis where you can see this at 570 or 73, this conversion takes place. And you can see that when for that actually we use this heating attachment available with the XRD, and when you increase temperature, and we actually narrow down the scanning temperature from 570 to 575, and you can see that around 572 this conversion takes place. And while alpha quartz composition reduced, the beta quartz is increasing. And after conversion, the change of unit volume cell is very less. So you can see that phase conversion takes place between 572 to 574, and crystal lattice was further established through the infinitesimal rearrangement of beta quartz. And when you take unit cell volume, a significant expansion of the unit cell volume is observed at 600. Okay. Actually, I am not discussing this in detail. That we have published this data. You can refer to these articles. It is available in website. But this, I want to emphasize here that actually we are expected to do applied research, and but however, when you do some kind of applied research, you are still finding some data that is worth publishing, and sometimes unexpected data. So that is what I want to emphasize. And also another important thing is that we have to use maximum of available facility. So we use our instrument for maximum usage. So that will ultimately produce valuable data, and still we can publish. So that is the important thing. And you can see is this microstructure changes. I won't talk about these things, but this is very essential because this electrochemical reaction takes place at about 500. So we want to see how their structures are behaving. So that is why we did this preliminary study. You can see that lattice strain increases to a certain level and again decreases. It depends on the method and the product. So here we use quartz. Like that, dislocation density decrease and increase. So like that. So overall, it shows that microanalysis relevant to phase transformation quartz evidently provides a better picture of the structural rearrangement of the crystal lattice. A sudden increase in lattice strain close to the phase transit temperature is probably due to vigorous vibration of atom. The strain is due to actually vibration of atom within the crystal structure, the crystals, unit cells. Okay, and the size compatibility therefore suggests the transition should proceed through an intermediate to maintain the uniform arrangement of the structure during the conversion from alpha to beta without being significantly altered the number of crystal defects. So these are some findings, and you can see this here also we have employed Williamson-Hall method to calculate the micro strain, and you know at 573 the scatter is almost very not widely scattered, they are narrowly scattered. That means we have produced uniform. That means the structure is uniform and stable structure has been formed. And this is the thermographic analysis of quartz. You can see at about 573 the conversion. And okay. And conclusive remarks, as I mentioned, that substantial change in the composition of quartz was observed between the temperature 572 to 574. And it is evident that the phase transformation initiated with the low amount of beta quartz at around 572, and one increment of 1 centigrade increment in temperature is accounted for significantly change in composition. And the present study further revealed the maximum lattice strain and crystalline observed at the beginning of the phase transformation. Like that, we have analyzed this microstructure. So like that, I won't go detail in this thing. Here also we use calcium chloride where we use this as an electrolyte in our reactor, we also study the hydration, dehydration properties at this elevated temperature. I will just briefly go through. And this is the normal hydrated calcium chloride, and this is anhydrous or calcium chloride without water. And this is we study at different temperatures using this XRD. And there also we observed their microstrain, how they behave, and corresponding microstructure. Now you can see the XRD spectra for calcium chloride at room temperature and elevated temperature like 150, and gradual conformation of hydrated calcium chloride to anhydrous calcium chloride. And here this shows this thermographic analysis of calcium chloride. This conversion takes place at two distinct temperature like 150 and 150. Okay, and above that you will have anhydrous calcium chloride. And there, the different phases can be observed at different temperatures. Like 150, you can have different phases with different unit volume cell. And so you can see this crystalline size also not much affected, and you can see different strain changes because of this vibration, the atom's vibration when you increase the temperature. And so this is actually a conclusive graphically conclude remarks of this study. You can at 200 you can have complete dehydration. There also we studied this microstrain analysis using the Williams-Morse method. So so these are publication actually for these preliminary studies. We have published in Powder Technology and Journal of Physics and Chemistry. Please refer these things. So I think actually I would like to thank our chairman and the PG for providing us funds for these projects. Actually, we have 3-4 projects is currently going on, and I don't know, Manu, can I have a few more minutes?
Yes, sir. You can talk.
Okay. Now, actually, these are the major projects, and the research work are based on material science and engineering. And I would like to also share another study that we have completed, and still some problems are being addressed. Can you see this presentation?
No, sir.
Is it you can see development of self-cleaning?
It's not visible.
Just now it's visible. Hello. Can
yes,
you see?
sir. It is visible now.
Okay.
Yes.
Now this is another study actually we have done some time ago. Actually, one of the companies, the ceramic companies, collaborated with us to develop a self-cleaning type based on nanomaterials. There are actually more studies are going on this area, developing self-cleaning materials and with antimicrobial property. So I won't explain these things because these are freely available. You can see. What we want to develop here is a type, because that the ceramic industry where high temperature is employed. Normally they fire at 1000 or maybe 1200, and this nanometer, especially this titanium, is not withstand that much of temperature. They convert to this less photocatalytic effect, less photocatalytic material of rutile at some mild temperature, about 500, it turns to the rutile nature. So here, one of the challenges we had was to mitigate this transition, because we have to apply this nanomaterial on ceramics and fire at high temperature. So I think we have been success in certain extent to reduce this conversion of an anatasiform to rutile. Now, I just briefly, I won't discuss the thing. You know that the potential areas of this, self-cleaning and antibacterial, ceramic glass, etc. And you can see this XRD spectrum above 500. This anatase turns to rutile. That is photocatalytic, not much efficient. So they are very less sensitive photocatalytic. So therefore, we have to maintain this anatase form. So there actually we develop a method to mitigate this conversion. Anatase rutile. There actually you can see these temperatures about 750. You can have anatase form, but above 500, the anatase completely goes and you will have rutile. But here we are succeeding obtaining this anatase type TiO2 to withstand high temperature. So that is a very good finding of this research. And actually, we have done a lot of factory trials at this factory. I will show now. This is actually some of the prototypes research to see, observe this self-cleaning and antibacterial effect. And now, so this is you can see this. We have used the screen printing and rotary method to apply this screen on this tile and fire at high temperatures. And we also actually did some antibacterial effect. We observed that the microbes are not grown on these surfaces. So like that, this is actually now, I would say 80% to 90% completed. Some discussion are going on. When it comes to commercialization, so there are some issues to be sorted out. So we are working on that, and this is what I want to stress some of our research at Material Techno section. I think with that, I can conclude this my presentation on this initiatives of research on mineral. With that, I thank Professor Rinda and Dr. Bhanudas Naik for giving us this opportunity to share some of our experience with you. So thank you very much.
Thank you, sir, for delivering a very resourceful and informative scientific findings on your research work. It will definitely help and motivate us, and the insights given on material research initiative will help us at large. Now the session is open for question answer. Sir, there is one question from Sonia Parsekar. What is the particle size of the clay particle binders using nanocomposites?
Actually, we observed under SEM, it is about, I would say, 20 nanometers. Hello?
Sir?
Can you hear me?
Yes, yes.
Yeah, 10 to 20 nanometers in size.
Okay. Thank you, sir. There is one more question from Ms. Monica Ghadi.
Yeah.
Commercial production of graphene oxide facility is available at your institute? She is asking, is commercial production of graphene oxide facility is available?
Yes, we have actually set up a process, the facility to produce graphite oxide, especially graphite oxide and graphene. And yeah, actually, there were some requests from customers. I think we have sold out. Yeah, it is available at Material Techno section.
Okay, thank you, sir. There is one more question from Ms. Ritika. What is the best form of silica to take during carbothermal reduction and why?
Carbothermal reaction, you mostly use silica sand. Okay, it's a sand form, but it is better use nano. When you reduce more particle size more, then it is beneficial because carbothermic reaction happening at high temperatures. I think maybe 1,800 or 2,000. So therefore, in order to this reaction takes place, the breaking of SiO2 bond, it is better to have silica particles as small as possible. Mostly it is silica sand.
Okay. Any more questions from audience? Okay. Thank you once again, sir, on behalf of all participants.
Thank you.
Participants are requested to take a note of the feedback link which has been posted in the chat box. Kindly fill the feedback form and submit. You will receive the e-certificate via email. Now I request all the participants to kindly put on their camera as we want to take a screenshot as a memory of this international webinar. Participants, kindly put on your camera as we want to take a screenshot. Uh, I request Dr. Chinthan Manoratne to please stop presenting, sir, your slides. Yes, yes. Thank you, sir. Okay, we are done. Thank you, all the participants. And I request all the participants to put off their camera now. And now I invite Mrs. Varsha Virjinkar, Head, Department of Chemistry, DCT's Dhempe College of Arts and Science, to propose vote of thanks.
Thank you, Durga. After the active deliberations of the international webinar on advances in material chemistry and applications, I take this opportunity to first and foremost thank all the resource persons, Professor Robert A. Burrow, Dr. Rupesh K.Mishra, and Dr. Chinthan H.Manoratne, who accepted our invitation graciously and consented to illuminate us with their thorough knowledge and expertise on their respective topics. I sincerely thank the management of Dhempe Charities Trust, Chairman Sri Srinivas Dhempe, and Trustee Madam Pallavi Dhempe for their wholehearted support for the smooth conduct of this international webinar. I profusely thank Sri Rajesh Bhatikar, Administrator, Dhempe Charities Trust, and Professor Vrinda Borkar, Principal, for their unending cooperation and belief in our efforts to conduct this webinar. I also thank all the participants for their active participation in the webinar. Last but not the least, I would like to thank all my colleagues in the chemistry department, as well as the administrative staff and systems administrator who worked tirelessly to conduct a successful webinar. Thank you all and have a nice day.